All right, week 107. What's up, everyone? Welcome to week 107 of building my own operating system. Today we are continuing with interrupts. What's up, Cat Flare? Nice to see you. Am I stream lagging today? Okay. What's up, Cat Flare? Appreciate you being punctual as always. How are you doing? Hope you're having a good Sunday. Yeah. Let me just get my chat window set up. Yeah, thanks for sending me those updates on Sir Chat, by the way. Sorry I didn't get to reply. You've been doing a lot of work on that lately. Yeah, maybe someday we'll switch over to it for the Discord server, for the offline Lark Discord server. I'm still sticking with Discord just for the moment. But yeah, but it's good to know there's options. Fixing vulnerability. Forgot about everyone's pseudo role. Yeah, I guess there's a lot of security things, considerations for all these roles and stuff like that. Okay, let's see. Where is the kernel at? I haven't worked on this at all since last week. If I recall correctly, we were handling software interrupts. And that seems to be working. So let's ignore this. Yeah. We have been working on interrupts, and the latest state of the art. I was curious to try to handle a software generated interrupt via the int instruction. Because those have the nice property that they, after you return from the interrupt, they continue execution after the faulting instruction. And so the test is just like we hit this int 32, and then we continue past and hit reached end of kernel, and that's what we're seeing here. Yeah, so also we just had this little test here triggering the GP faults and just checking what is our handle. I think we just do a panic, so let's just demo that real quick. Yep, we can see it hitting the GP fault handler. What's up, Night Walker? Hello, sir. Hello back to you also. All right, so what's up with the chat widget today? I'm starting to get a little bit concerned. We're not seeing any chat messages. That's a little bit unusual. Chat widget has been quite stable lately, and the stream is public, so not quite sure what's going on there. I'm up. Nice. Okay, well, if the chat widget doesn't appear today, that's too bad. Hope it's having a nice day wherever it is. Yeah, I think I want to focus on my work today. Yeah, I want to lock in a little bit more on this interrupt stuff. So anyway, that's the state of the art. We were able to use this strange method of triggering a GP fault. I'm just going to save this stash this off to the side because it's kind of a nice little code snippet to have around. Yeah, I'm going to try to just, as usual, I need to figure out what my one piece of progress is for today that I'm going to make. Configuring Raspberry Pi with Kali Linux. Nice. Got to do some hacker activities. Okay. So there's a couple I'm just going to do some brainstorming about how to potentially proceed here. Options are, I could obviously add handlers for more types of interrupts. That's kind of the very just basic option. We could just go in here and start adding more handlers. Yep. What's up, Anant? How much operating system building is completed? It's a very difficult question to answer because I don't even know. I don't even know really what the final end result is, but I know we want some basic. We need to have some basic functionality in place to have any kind of operating system. So I don't know. I don't know. For my arbitrary idea of an MVP where we have just a kernel, like completely kernel mode kernel, where we have kernel threads that are preemptively cooperative or preemptive multitasking with multi-core support, ultra minimal MVP. I feel like we're like 10% there or something like that. It's hard to estimate. I mean, we're surprisingly far along with our base functionality. Like we have some interrupt support. We have like a bit of virtual memory support prototyped, and getting a super simple scheduler is not the most impossible thing. Will you create your own C compiler in assembly and write another C compiler and compile it with your assembly written one and compile your OS? Yeah, it's probably next week if I had to guess. I'm probably going to make a lot of progress. Realistically, we're probably going to finish the OS this stream actually, and so we'll have time to move on to a lot of more projects after this OS is done. So Frizzle. The OS currently cannot run anything. It's still super early stages. We're just trying to kind of boot up, get everything going. So yeah, no applications in sight at the moment. Engineer it to remove boilerplate. This is another idea that's a little bit more interesting. Yes, using Clang. Yeah, these are some options. We could try to software engineer the interrupt implementation a little bit more. I'm just wondering if there's any more pressing interrupts that would be interesting. But the thing is, what's nice is we're already handling GP faults. And so in a lot of cases, the kernel is no longer boot looping. Oh, one second. Let me make sure I got my break timer running. Okay, give me 1 second. So, yeah, the nice thing is we're no longer boot looping on everything, which is quite nice. And so, I don't know if there's any more super critical interrupts we should register a handler for necessarily. We have many unfilled slots. All right, did this chat widget appear yet? The chat widget did not appear yet. Oh my gosh. Looks like we're going with a chat widgetless stream today. Too bad. I'm not sure if I can do anything to fix that in the moment, so that's a bit unfortunate. But anyway, yeah, back to this. So I was just thinking if there's any more interrupts we should urgently add a handler for, but I don't really think so. I'm not. Maybe the double fault, but we're already handling the GP fault in a way that doesn't double fault. So, I mean, actually, one thing I would be kind of interested to see actually is just observing the double fault handler running at all. I don't know if I've quite seen that before. And so one fun experiment that we could try is let's cause a double fault. Let's really observe a double fault. And unfortunately, this is going to involve all of this boilerplate. So this is also a good opportunity to reconnect with and to sort of get a better sense of what is the amount of boilerplate needed to add a new interrupt handler. It's touching many places in the code. We need to touch this assembly macro. We need to add a constant here. We need to add a prototype here. We need to go over here and adjust the IDT construction. We need to then go over to the handle trap function and add a dispatch. And then finally, we need to add a function to call into it. And so that's sort of what I'm talking about with try to software engineer it to remove the boilerplate. I would just be interested in how we can improve this implementation such that it's a little bit easier to add interrupt handlers, which is just kind of a software engineering thing, but I think that is an interesting topic. So let's just get kind of warmed up. Let's just go ahead. Let's add the double fault handler in so we can just check out what a double fault looks like in the wild. And I just need to refresh on what the actual number is. It is number 8. So we got double fault. Double fault stub. That's just how I'm naming these. And the naming is super inconsistent right now. I'm using EXC, which stands for exception, because I thought that exceptions in some ways was a bit of a more generic terminology around interrupts versus traps versus faults. Like it's quite a bit of terminology, but I'm kind of reconsidering that because I don't know. Exception is kind of confusing because it's easy to get confused with C++ exceptions, especially since I am using C++. So now I did the change to the IDT, and I did this wrong. Double fault. No, wait. Okay, I'm not sure why the IntelliSense did not complete that correctly. So now we got the stub. Now we need to actually declare the stub. And does it have an error? Yes. And it's 0. Okay, interesting. So we need trap stub double fault. And it's number 8. Yes, and it's number 8. Interesting. It's always 0. Is that what that means? I'm just gonna ask the AI real quick. Does x86-64 double fault push a 0 error code always? Yes, df pushes an error code of 0. Okay, good to know. So let's, yeah, so we basically added the stub now, and then now we can finally we can pop into here and fill out the boilerplate double false. And, oops, okay, double false. And then now we're here, and we can finally say double false. We're not going to trap return. We're just going to do this, panic with the double false. And now what I'm going to do is, now we ostensibly have the double fault handler registered. In order to observe the double fault in real life, we need to first, I believe, trigger the GP faults. And then somewhere in our handling of the GP faults, we need to trigger another GP fault, which I believe triggers the double fault. But maybe it's worth checking the manual to really understand that a bit better. What's up, Digitalize? Nice to see you. Let's like really understand what a double fault means. And as usual, I'm going to spend a limited time budget to see if I can like raw dog it in the manual and see where they talk about double faults. I mean, my first guess, I'm going to go over to this thing and see it's interrupt number 8. So let's learn about the double fault. I'll just, as usual, grab the screenshot just to make that easy to find later. All right, indicates that the processor detected a second exception while calling an exception handler for a prior exception. Let me just check the OBS also to make sure the audio quality is good. All right, should be all right. Yeah, so we're handling exception, and then bam, something happened where another exception happened. Normally, when the processor detects another exception while trying to call an exception handler, the two exceptions can be handled serially. Okay, so that, right. And that's sort of like an example of this is if you're handling a page fault and then an interrupt comes in. I want to say that could be one example of that. Although strictly speaking, the page fault handler doesn't need to disable interrupts. So are you developing basic IRQ handlers for today? Sort of, yeah. We're continuing to just kind of play with the IRQ handlers. So in the last couple of streams, I have some basic interrupt handling infrastructure that's created. Like I can create an IDT, which I construct in this way. And then I'm able to kind of do a stupid switch statement and then handle the different kinds of interrupts that can come in. So that's still sort of the vibe. It's like kind of working. And I would like to improve the ergonomics around these APIs, and like currently there's a significant amount of boilerplate needed to handle an interrupt, and so that's in general what I'm kind of curious about looking into. But before I get to that, I was specifically curious about the double fault exception and just learning a little bit about that because that's kind of an interesting one. So normally when another exception happens while calling an exception handler, they can be handled serially. However, the processor cannot handle them serially. It signals the double fault exception To determine when two faults need to be signaled, the processor divides the exceptions into 3 classes: benign, contributory, and page faults. This table shows the various combinations of exception classes that cause a double fault to be generated. Yeah, I think there's a lot of opportunities digitalized to clean it up especially using C++. I'm not. Yeah, I don't know the exact form. I think it'll take a bit of experimentation to play with different implementations, but I feel like we could get something that looks kind of clean, looks kind of nice. Yeah. Okay. So there's apparently double faults are generated under specific conditions, and it's not just anytime an exception happens while there's another exception. It's particular combinations of things. So maybe it's interesting to learn a little bit more about. So it's so in general, it's an abort. The program cannot be restarted or resumed. The handler collects diagnostics and basically just shuts things down. So let's conditions for generating a double fault. If the first, right, it's like whether these categories happen. If the first exception is a benign and then another one is a benign, it handles them serially. That's kind of interesting. What's a basic example of that? So benign is like all these things like a breakpoint interrupt, invalid opcode, software interrupt, floating point, debug interrupt, contributory. These are like a bit more serious, perhaps, of the divide error. GP faults. What is a control protection fault? Oh, is this is a new exception that's introduced for the control flow integrity stuff, maybe. IRET, or these quite exotic instructions. If you have indirect branch tracking, this exception can be generated due to a missing end branch instruction. Okay, so this is like when an exploit mitigation triggers this. Like when an exploit is running and it's triggering a kind of like a invalid indirect branch, or even like it's like trying to ROP or something. But then if this is enabled, then you get a control protection exception. So it's like quite more advanced and exotic than what we're dealing with currently. That's kind of interesting. Lastly, page faults are their own category, and apparently virtualization exceptions are also considered this category. And so let's see. So basically, if something happens and then a benign fault happens, nothing special happens. You just handle them serially. But then things get more interesting. If you have like a contributory and then another contributory, then you get the double fault. If you have the page fault and then a contributory, you get the double fault. Okay, so if another benign error still wastes cycles, I mean, yeah, it's doing something. If another contributory or page fault exception occurs while attempting to call the double fault handler. The processor enters a shutdown mode. This mode is similar to the state following execution of a halt. It stops executing instructions until a few particular conditions. Special interrupts happen. So, okay, so this is this is hardcore failure mode. If you get the double fault and then you get a contributory fault or a page fault, yeah, things are going crazy. So let's do a simple example. Let's generate a double fault via this entry in the matrix. We're going to do a contributory exception and then another contributory exception, and we just need to choose which contributory exception we want to use. And actually the cool thing is we have different options: divide error or a GP fault. Divide error is a little bit easier to trigger, so I'm going to go with that one. What's up, Shanking Disaster? This is the ALU part you're working on. This is interrupts and exceptions. What's up, Nicolas? Do you have a degree? Yeah, I have a degree in computer engineering, a bachelor's degree, but I didn't learn any of this stuff in my degree. Yeah. What's up, Sooks? Nice to see you. So yeah, we're on a mission to generate a double fault. Okay. And so here we're going to generate a double fault via a divide by 0. We're going to kick in our divide by 0. And then what we're going to do is in the handle divide error, we are going to do another divide by 0. And this should trigger the double fault. We're going to flow down here. Bam, hit the divide by 0. It's going to flow into handle trap, to handle divide by error. And then we're going to hit another divide by 0. And my expectation is then we're going to flow into handle double fault. And we're going to panic on this double fault print. Let's just run that real quick. Okay, undefined symbol, because I apparently X double faults dub, that would do it. I forgot the naming. And that shows you why it's annoying. Oh. Okay, we are boot looping. Or are we? Hard to tell, maybe. Okay, that was not what I expected. Why did that happen? I'm gonna break on handle divide error. Okay, now we're there, and let's just carefully step it through. So eyes over. Okay, we got a couple instructions. So. Oh wait, no, I need to return. Okay. Oh, fin. Yeah, so we got 2 instructions. So we're going to hit the divide, and then let's just see where we end up. I mean, it's not even that necessary. So now we're in the divide error stub, and it's time for the quick 20 seconds. So I'll be right back. So we appear to, again, be in the divide error. And let's just see what happens. So we're going to step instruction. And then, so right here, we are pointed exactly at the divide by 0. So is a machine reset going to happen? No. What happened? We appear to be in an infinite loop of divide by zeros. That's what's happening. We are, which kind of makes sense. Okay, that kind of makes sense because, yeah, we triggered a divide by 0, and then in the handler, we're just doing another divide by 0. So it's possible that I misinterpreted this diagram. I think it really needs to be a second unique type of exception, I guess, if I'm understanding that correctly. So it's not sufficient to just trigger a divide by 0 while you're handling the divide by 0. You need to choose another one. And currently the only other one that I really know how to trigger right now is the GP fault. So let's go ahead and do that. I'm going to replace the divide by 0 with a GP fault. This is going to trigger a GP fault. And let's try that. Maybe that is going to reproduce the double fault. That did not reproduce. Oh, that did not reproduce. Okay, let me take some notes. So, tried div 0, div 0. That just caused infinite div 0 loop. We're trying the div 0 GP fault. This simply handled the GP fault. So this is not what I expected. Div by 0, we triggered a divide by 0, and right here, and then here we triggered the GP fault. And for some reason, it's just simply handling the GP fault. We're not seeing the double fault. I want to see the double fault. And so this would appear, it seems like it's handling exceptions serially. Even though I believe I'm doing it right, if the first exception is a contributory exception, the second one is contributory, generate a double fault. We are not seeing that. And so I have some ideas about why this could be. Is it a Kimu thing? Does Kimu emulate this accurately? Or what else could be the problem? I'm going to check the chat. Nightwalker is saying, what setup are you using and how do I create my own and start little by little learning OS dev? Yeah, I'm using this like setup that I've been making over the last 2 years. Yeah, and it's based off of this MIT OS, which I heavily modified. I don't know if it'll be so valuable to you, but for the moment, my recommendation would be to check out these open source university courses like Harvard, I think 61 or something like that, has some OS stuff. So the nice thing about these OSs is that they sort of already work a little bit. The problem is that they sometimes work too much, and you don't want them to do everything for you. But I want to take a note about that's an interesting question about, yeah, like own little environment. I could think about maybe releasing some limited portion of what I have going on. Yeah, I could consider that. So I was assuming you were trying to error check them. That's why I mentioned ALU. Are you trying to force these faults for something in particular? So I am just trying to observe a double fault. That's really all. I just want to test out what it's like to handle a double fault, because it's a fairly unique and interesting exception. Yeah. Thank you, Tanvir. Okay, yeah, let's okay, then I'm gonna immediately pop into the AI. Does Kimu accurately emulate double faults? I am triggering divide by 0. And then in my CPP handler, I trigger a GP fault, and it doesn't produce a double fault like I expect. Oh, the DF only occurs when a second exception happens during delivery of the first. Or the CPU can't invoke the handler. If your DE handler runs and then your code triggers GP, that's just a nested GP, not a DF. To force DF, make the second fault happen while delivering the first. Okay, so I was understanding this incorrectly. So yeah, to really make sure this happens, make the second fault happen while delivering the first. I think that's the key question. So while delivering the divide by 0, I need to okay, so maybe that's so if I corrupt the IDT entry, potentially, or even have a missing IDT entry. So let's try this. Let's comment out the divide error. Let's comment out the GP fault handler. So okay, maybe step by step. Let's comment out the divide handler, but leave in the GP fault. What's going to happen when we trigger a divide by 0, but we don't have a divide handler? My guess is that we're going to see a GP fault. Oh. Okay, jump scare. The double fault appeared. Whoa. Why is this so small? Okay. Huh, interesting. So triggering the div by 0 without a div 0 handler, double fault. Let's make sure we understand why that happened. And so we triggered the divide by 0. And then it's trying to it's trying to deliver this interrupt, but there's an invalid IDT entry. The IDT entry is invalid. And so then what happens next? I think it triggers a GP. Let me just ask the AI just to be clear. Okay, so I triggered a div by 0 without having a valid divide error handler. How does this end? It caused a double fault. Why? Is this because the lack of IDT entry caused a GP fault internally, which was the second exception needed to satisfy triggering a double fault? I think there's this internal GP fault. Yes, DE occurs, and the CPU can't deliver it because the IDT entry is missing. The delivery itself triggers another fault. GP. A fault during exception delivery produces DF. Okay. Or NP. What does NP stand for again? NP. NM. Segment not present. Okay, that's a weird one. Okay. Okay, this is cool though. So we've successfully handled the double fault, and I'm just curious what happens. So then my next question, what happens if we remove the double fault handler and we trigger the divide by 0? So we have no divide by 0 handler. We also have no double fault handler. Is it going to boot loop, or is it going to trigger a GP fault? Okay, my guess is that it's going to boot loop because it's going to, yeah, for whatever reason, having a GP fault handler was not relevant here. Even though we have one, it's still called the double fault handler. And so I'm just assuming that if what's the chart say? We have the contributory first one, and then we have the GP fault, I think, because it can't handle the divide by 0, which triggers a double fault, but then we don't have a double fault handler. So what's that gonna do? Then maybe it does the shutdown mode or something. I don't know, let's just run it. Okay. Yeah, look at that, we're boot looping. Pretty confident we're boot looping right now. So that is interesting. So the presence of the GP fault handler does not do anything in this case. Yeah, even though we have a GP fault handler, it doesn't matter. It'll still boot loop. So the main point is that the usefulness of the double fault handler is to protect against when you have an interrupt or an exception into an invalid slot, I believe. Because that's exactly what we were seeing before. We're triggering this divide by 0 into our invalid slot in the IDT. And if we don't have the double fault handler, we boot loop. But if we do have one, at least we safely catch it and print double fault. So really my goal is to avoid boot loops on errors. That's, you know, that means that's the worst case basically. And so we're trying to at least put some basic protections in place to prevent us from getting there. And the most basic forms of protections are having, well, first the GP fault handler, because a lot of things trigger, like if you have, like a lot of things just generally trigger GP faults when things go wrong. And so that's important. And then as an extra layer of protection, the double fault handler, specifically for when problems happen in the process of handling exceptions. And that helps catch those issues. And so with the combination of both of these handlers, we're in a much better position to not get weird system reboots, even if things go pretty badly with the kernel and it crashes in weird ways with strange errors. We should not see too many of these crazy boot loops anymore. So, yeah. Okay, well, cool. Let's just bring it back. And that's going to be my takeaway. I'm just going to recap this a little bit. So, okay. So if you trigger an exception with an invalid IDT slot, it triggers DF, even if you have a GP handler. So that was the learning there. So DF handler protects you against interrupts or exceptions that fire against empty IDT slots. Otherwise, you boot loop. Okay. Okay, I would consider that kind of a nice little piece of learning that we did. Seeing a DF handler appear in the wild, in real life. That's pretty cool. Give me one second, I'll be right back. Okay, so that was pretty cool. What's next is the question. I think it's time to get into some of the software engineering. Try to software engineer it to remove boilerplate. Let's check that out. So I'm just gonna go ahead with a little commit. And okay, so a bunch of this stuff is not necessary anymore. Just gonna delete all of this, I think. Sorry, wait. We don't need this hunk. We do want this one. Yeah, we do want the basic stuff for handling the double fault. Don't need this. Want this. Yeah, it turns out we didn't really need that. And then we want this. Yeah, none of this needs to go in this commit. We just want the commit, the parts that add a double fault handling. Okay, so add df handler. Okay, cool. So let's move on. Let's talk software engineering. Lost connection. How do I quit? Okay. Okay. Oh, just in time for the break. What's up, Ismail? Okay. Yeah, another day of kernel development. Okay, so here's what we're talking about. Try to software engineer it to remove boilerplate. This is the situation. Currently, to add, or maybe even let me clean up my working tree a little bit. I was just kind of playing around with some ideas. I mean, this might be relevant for what we're doing right now, so I'll just keep this in. I will drop this hunk. I'll drop this hunk too. Yeah. Or comment panics. Nice, clean, relatively clean working tree. So let's talk software engineering. It's one thing to implement a sloppy, messy kernel that technically kind of handles interrupts, which is what I currently have. But it's another thing to try to make it good and make it a little bit better. Make the code a little bit nicer. So let's think about this. Okay. I'm gonna pull down, get some more room. And so let's just understand the process for adding interrupt handlers. First, you need to add a stub, one of these like macros to create the stub. So there's a couple components here, and maybe I can use a red sticky for some of these problems while I'm at it. But maybe just in terms of components. So, right, there's the stub. There's this notion of the stub. That's this thing. There is the IDT plus entries. And then there is the handler. So these are the three primary. There's also some random junk over here for some like constants which are needed over here, as well as over here. So we have some duplication of the int number, which is a problem. Yeah, just to flesh out the example. Oops. And then the final piece of the puzzle is these functions. And so then these columns are here. So so this is technically the dispatch. Actually, no, wait, yeah, I wasn't done. There's the dispatch, and then the actual handler. So there's like 4 of these pieces that you need to touch to make this work. So yeah. And so, yeah, there's a lot of different, there's quite a few different problems. And so I'm just going to jump to some solutions without even thinking. And so I'm just going to brainstorm. So obviously, like jump table, or if like maybe I'll call it a function pointer table is one natural kind of solution for at least this kind of thing. Yeah, Ismail, what out of the loop, what kind of interrupts? These, it's pretty much, yeah, these 3 are the ones we have. Pretty sure that's accurate. Okay, never mind. I need to update. In the meantime, we have added the double fault handler. So this is basically what we have right now. Divide by 0 handler, general protection fault or GP fault, double fault, and then this thing, I'm calling it the syscall. It's not really a syscall right now. It's pretty much, it's just a software interrupt handler. So software interrupts are these things where you have these int instructions, and code that's running software can trigger a software interrupt via an int instruction. And this is how legacy system calls work on a lot of operating systems, or in general, this is how legacy system calls work. It's like it's an interrupt. In modern day, we don't use these anymore for system calls. We use like more direct processor features to support system calls. But this is the old school way of doing system calls. It's just an arbitrary software interrupt. And so we have support for software interrupt number 32 specifically, and which I'm just like calling system call, syscall. We got four different things. And so yeah, problem is, so we got problem number 1 is like dispatch of the interrupt number. So we have these numbers over here, and it's duplicated with these numbers over here. And maybe my arrows can be a bit bigger. And the thing is, these numbers get used over here, because what we're doing here is I'm constructing an interrupt descriptor table, and I'm constructing it with these simple structs that just have a interrupt number and a function pointer. And then the actual constructor of the IDT goes through all of these things and then registers the function pointer at the appropriate index into the IDT. Which is how I've currently opted to implement it. I think it's kind of a clean, fairly clean API, because the details of exactly what interrupt entries exist is not hard-coded within the IDT class. You pass it, you at the caller of the class passes in what it wants to be in there. So anyway, that's like these numbers get duplicated. So that's problem number 1. Number 2 is like this dispatch. Yeah, maybe it's annoying to adjust the switch case. On the other hand, how often are we really going to do this? And also, are there really alternatives? And so, just to sketch it out, yeah, instead of a switch case, we could have some kind of function pointer table. I mean, the funny thing is, like, there's like, it's sort of like there's different levels of function pointer tables. The IDT is basically a function pointer table. It has other metadata, but it's basically, yeah. But all these entries point only to the stub. And maybe it's worth having a screenshot of the stub. So we can't really use the IDT as like the ultimate function pointer table for handling it like this, because it's just a bit too raw. Yeah, the purpose of like all these stubs is just to kind of do a minimal amount of work, construct the trap frame, call into the generic handling infrastructure here, at which point we can then again do a second dispatch on the interrupt number, I think, and do something like that. So that's kind of what I'm thinking. And so yeah, this is not like mind-blowing or anything like that, but somewhere, I don't even know where we would store this table. I mean, the worst way is just making it global, but you could imagine some kind of code where we get like, I don't know, somewhere there's a reference to the table, trap handler table or something like that. We get a table, and then we can dispatch, or we can like call trap frame dot interrupt number and something like that, and we can call the entry at yeah, something like this. I mean, the real like stupider version is like you just get you like just index into the table at interrupt number, and then you just call pfunc with whatever you want to pass. And in our case, we seem to be passing the trap frame to everything. Maybe the downside of this is that I don't know if it, like with this, it's quite flexible. Like these functions can take different arguments, and we might lose some of that flexibility if we go for the function pointer table. Or do you, I don't, yeah, function point. I mean, function pointers have a specific signature. Yeah, I'm not super sure on that one. So I'm just gonna ask the AI, if I make a function pointer table, do all the functions need to follow the same prototype args? I think they do, right? Because you just make an array of like of function pointers, and then maybe you can like do some casting things to if you need, you can always maybe like do some casting tricks to, yeah, like kind of break out of that, but by default, sort of like that. Untrap entry point, right? Okay. So I don't know. The thing is, this is also not so painful at the current moment, but it requires, again, you need to use this number and switch on the number. Yeah. Yeah, some previous example in the code where you do something similar. I don't. Certainly not in this kernel, because the kernel has almost nothing. And if we go back to reference JOS, which is always a possibility, JOS does kind of this stupid thing and has a big switch statement. It has like multiple, but it's basically, yeah, this is the equivalent code in JOS, which is almost exactly the same as what we have now. And yeah, I was probably sort of channeling a bit of it on writing my own stuff. So let's maybe I'm not, I'm not like completely certain about if, this is not so bad. Yeah, okay. I don't want to take too long. What I'm maybe okay, before diving too deep into that, there's like some other issues here. So let's just like keep a holistic picture. It's like, so what about this thing? These stubs are really interesting. So maybe I can also just try to imagine what would be a nice API. And that's kind of what I tried to do over here, where we want to have some kind of isolated container that expresses like the number of the interrupt, has a stub, and then also has a handler. The actual handler function, and like sort of kind of grouping these things together. Right now, the information is very distributed. We have these constants over here. We have the stub over here. We have the actual dispatch over here. So constant lace. This is not, it's not really from scratch. I mean, I started out with this MIT course, but I've heavily, well, I mean, yeah, I've so heavily modified it that basically nothing, there's still some components of it, but it's basically mostly from scratch at this point, with some exceptions, like this stuff is all from JOS, these macros that I'm using, so some bits do still exist. So, right, so a couple of things are kind of annoying. It's kind of annoying to have to declare these function prototypes independently. So we have this stub that's kind of generated over here, but then in order to access it from C++ code, we always need to have a prototype somewhere. And so maybe that's an interesting thing to think about as a first step. How might we reduce the need to annoying manual prototype? Yeah, I think this is where it starts just to get kind of creative. You just need to think about how you want to do it. And it's time for the 20-second break, so be right back. Yeah, so like for me, it's sort of like a macro is sort of the idea. What if we have some kind of macro that generates this prototype, but then also somehow generates even this? Like, I'm sort of interested in how we can hoist this out of this assembly file and actually do it more in a C++ file. Let's play with that a little bit. Like, so let's say we want to take one of these stubs and not have it live in this .s file. Because if we can somehow manage to generate the stub here, we can then have some macro that could generate like both of these things. Like the macro would look something like, oops. It's like stub macro or something like this, and then it's something like exe. I mean, it would be pretty much the exact same thing we do over here. I mean, actually, no, it would look like stub macro or whatever. We do this over here somehow, and it generates this thing, and somehow this function is going to be our stub. And I think we can use a naked function for this. Naked functions are these exotic things I like almost never, like I've literally never used a naked function before because they're super exotic, but they're functions that just don't have a prologue and an epilogue, I think. And they basically allow you to get basically just have like assembly instructions without a prologue or epilogue. So I wonder if we can do that. And I think I need to ask for a little bit of help from the AI to do this, but that's sort of my current idea. So I'm just going to express my vision. I think we want to have some kind of macro. We pass this and then it generates this. And so it needs to be an inline because this is going to live in the header. But I think that's not a problem because these stubs are not really going to be used in a lot of different places. So let's clang naked function. This is a naked attribute. Oh, this is the proposal. And the Chris Latner seems pretty reasonable to me. Okay, where naked? GNU has it also. No documentation. Big Chris approval. This attribute tells the compiler the function is an embedded assembly function. You can write the body of the function entirely. I mean, but this is, I don't know even know what compiler we're talking about here, but I think this, I don't know what compiler this is, but that's the idea. And I've never used this before. But I have heard of it, and apparently it's impossible to find documentation about this, but no, wait, like what? There's gotta be something. But all I can find is these exotic compilers that are talking about it. Dang, okay, cookies, okay. When naked, it informs the compiler the function is written entirely in assembly language. It will not generate function prologue or epilogue. So my question, because that's sort of what we want. We just want a stub, and the stub is really simple. It has 3 instructions. It has either 3 or 2 instructions, a push and then a jump. This thing is okay to still live in assembly, or is it? Because then call trap handle entry point. Are we including something? I sort of forget how this even, I think this is just purely at the linker level somehow. Like you don't need to include a header. It just emits a call to this symbol, and we just need to make sure to have this symbol in the binary for linking, I think. Right, okay. Let me just, I have an idea, I think. Yeah. I think the ARM block was referring to the ARMclang compiler itself. Oh. Maybe. I mean, I don't even know what compiler it would be talking about. ARMclang. But I think the general premise is like still works. So that's my creative idea at reducing a bit of this boilerplate. The embedded compiler for ARM. Oh, really? Okay. Let's just see what the AI thinks of this idea. Don't code. Would it be possible to reduce boilerplate by having a macro that generates the extern-c prototype for the interrupt stub, as well as the actual ASM stub by using an inline naked function in the HPP? The inline naked function simply needs to push a value and then jump to another stub symbol, which in this case is finalize trap frame and call generic handler. Let's just see what the AI thinks. I feel like this could be doable. But it's brittle. Inline. A compiler and ABI specific. The remote is still an S macro that emits real symbols. Okay, it's okay. And a site. Otherwise, is there any other way to avoid the boilerplate of manually adding a prototype? Use a single macro list in one header to generate all external C declarations. Showing, I don't know what it means. A single macro list. An X macro list to generate all external C from one source of truth. Try.hpp declare. Oh, stop. I think X macros are disgusting. Okay, wow. So we have this. Okay, so it's a strange file that has a bunch of these things, and then it sort of gets expanded out here with, okay, with this extern C block. Okay, I see. I'm just gonna screenshot this idea, this feedback. Also, thank you to A. Swazon for the comment from Bogota, Colombia. Thank you. So, okay, so this is like this kind of idea. You have all these, you just have this like kind of random file that happens to fit the macro. Why is it called an X macro though? That's just a random convention, right? And then you define this and it expands out. These macros are so ugly. Who use name in a table? I see. Okay. Interesting. So the idea is that, yeah, then you can declare, you can basically just use, you declare the data of like all the names just in this random file. And then you can have these locally defined X macros that do whatever you want with these strings. And you can generate prototypes with them if you want. Or do pretty much anything else. Okay, it's worth screenshotting the idea. Okay. Okay, at the very least, the extern C with the braces is a good idea. I didn't know you could really do that. So now what does this look like? So yeah, so now we just have like all these things, which is honestly not the worst thing in the world. Does it compile? It does not compile. What? No way. Oh wait, but I'm missing something. I'm missing this one. Okay. Okay, so compile. So, okay, so I don't know. My idea apparently got shot down a little bit. Are compiler and ABI specific? I want to challenge this a little bit. I'm still wondering about the inline naked function. It really just has to have two inline asm statements. One with a push instruction, another with a call. Their assembly stub symbol. Is this really that brittle? Naked is non-standard. Mark it with no. Okay. It seems to be shooting this down, unfortunately. So yeah. And I'm okay with that. Realistically, this infrastructure gets written sort of like once. It's not like we're like adding thousands or like so many new handlers, but I just wanted to spend a bit of time to think about if there was any possible way to improve this. And so far, this is like, yeah. Stanislaw got an OS class tomorrow. Okay, hope you're prepared. Some Doom's production. You've got to find a way to humble me. Nah, man. The computers are just so broad. There's so many things to learn about in computers. There's so many things I don't know about computers. I'm just going super deep in this strange area of computers, but yeah. Okay. So conclusions seem to be that, okay, this assembly stub in the .s file seems to be the way to do it. Just straight up. And we could try to go galaxy brain and do some crazy naked functions to be a little bit lazy and not have to type out all this stuff, but it's also not so bad, and there's a fairly limited number of these things anyway, so maybe this is clean enough. Problem, yeah, what do we do about these numbers? It would be really nice to share them over here, and I think that's what I want to do. Just question is can you including the constants over here? So I believe we can just do an include, or so I'm just gonna ask it okay, I'm just gonna ask it. So basically what I want to do, don't code, I want to share these constants with trap.s so I don't duplicate the numbers. My idea is make them defines, because assembler can't interpret inline const export auto from C++. Wrap this in an if-def, so the assembler doesn't see the rest of this file. Add and include in trap.s. That's what I'm thinking. Thoughts? Yeah. Or yeah, it's saying, yeah, the other way to do it is just make a new file, which is not a bad idea. Include it. Let's just go with that. So I'm just going to duplicate this file. I'll call it, it's going to be a .h file, and I'm just going to use defines for this one kind of exceptional case, because we're trying to include it from assembly. And what's the name of this file? I'm going to call it interrupt numbers.h. Okay, 20 seconds on the clock. Be right back. Okay. And apparently I messed this up. So yeah, still TBD on the naming of everything, but also I think I messed that up. It's 32 and 13. Okay. Okay. Okay, so let's just pretend like we did that. So we're going to include interrupt numbers.h. We're going to comment out all of this stuff. This is not, okay, yeah, my clang D is warning that this file is not actually used, which is actually right. So then over here, include interrupt numbers.h question mark. And then over in the K main, this is all, I'm going to predict this is not going to compile. But how is it finding these? Yeah, because right. Oops. Through this. Okay, so yeah. So if we get rid of this, then we need to go into K main. But I'm just going to keep. Okay, okay. For absolute cleanliness, let's just be more hygienic about it. This thing is going to directly include it for the moment. So now these things can get their numbers, and kernel compiles a no. Okay, and now, yeah. So, yeah, a lot of things like trap.cpp also depends on these constants right here. And so by removing it from trap.hpp, we were just creating a lot of problems. I think, you know, I'm gonna revert that. I don't feel so bad about just including this thing right here. Yeah. How to disable clang D warning on a line. No lint. Okay, I don't know with the no. I think the no lint did not reload window. Okay, it didn't seem to do anything. Wondering if it's easier to ASM interop in Rust compared to C++. I don't know. I mean, it's pretty easy to do ASM interrupt in C++ with just calling these symbols and stuff like this. I'm not sure, yeah. Okay, kernel builds and kernel runs. Reaching the kernel, looking good. So far, we just have a little bit of progress here, and then now we can go ahead and port these to use the defines in interrupt numbers.h. Can it do that? It did not do that correctly. Dang. Okay. Okay. Man, I suck at copy and pasting. Okay. Why did it do that? I'm gonna get this right. Oh my gosh. Sorry for making you watch this. Okay. Stupid. Okay. So we have the numbers there. Good. So that's a little bit nicer, right? So now this goes away. This thing, we're scrapping that idea. Yeah, so unfortunately, we can no longer use constexpr, inline constexpr anymore for these things, which is kind of unfortunate. Really, the only reason I was doing that before over here is because this is the idiomatic way to declare a constant in a header file in C++ in a way that doesn't trigger doesn't trigger a lot of copies of the number in every single translation unit, because in the naive version of this, if you don't use a define and you just have a variable equals 0, you're going to get a global variable in each translation unit. And so to counteract against that, you need to use inline. And then I don't remember the reason for constexpr. It's just something people do for these kind of constants because there's no reason not to, really, and it allows them to be used in constexpr contexts. And so, yeah, we cannot, but it's not really a massive deal. These numbers are not so widely used. They're used in very local contexts, and it's really just because they're used in this assembly file, which is why we need to use the define. So, yeah, I mean, the K thing is kind of weird, maybe. I don't know the naming about this quite yet, but that's not the most important detail. And so back to here. So we've sort of improved this a little bit. Let's get the picture. We've improved this one a little bit. This has pretty much totally stayed the same, which I think is kind of okay. I mean, this is not so interesting, but we can make it more, we don't need to include, actually, do we? Let me see. So this IDT thing, takes a list of IDT descriptor infos, which is a struct that has the index and the pointer right after it. And so I believe, yeah, so we can make it a bit cleaner. I just was thinking of using this syntax to make it a bit more obvious, but we really don't need to. So I'm just going to get rid of that. So this is now this is how it looks. This is how our IDT construction looks, which is pretty clean. We're just saying, hey IDT, I'd like you to have some entries. So at the k exec divide error index, please place the exec divide error stub pointer. At this index, please place this thing. At this index, please place this thing. And at a high level, that's what we're trying to do. And then the IDT class takes care of actually initializing, like doing the low level initialization, where it takes the offset. No, the offset is actually the function pointer. In this case, it's a little bit confusing. But we like loop through all of the entries, and then we index into the M descriptors, which is our array of IDT descriptors, and then we initialize it using the data in the entry, or in the IDT descriptor info thing. So yeah, that's how that looks, which I would say, I think I'm pretty happy with that. That's a fairly clean way to do it. It is kind of interesting. We're just constantly pairing these two things. We're pairing this number and the function pointer everywhere. I don't know. Yeah, it's sort of tempting to imagine, I don't know, maybe even more magical things, like some kind of object that includes both of these or something like this, and then you pass these objects. But this is quite readable, I want to say. You can just see, like, okay, what is this? This is the number. Okay, cool. What is this? This is this thing. Then you grep for this. And then you see it in the trap.s. Oh wow, a JOS file got modified at some point. Did that happen, right? A JOS file got, this is JOS, which I should probably delete all of this code at some point, because it's kind of getting in the way. But yeah, then you go over here and you see, okay, then you're like, okay, stub no error, and then you see the definition of the stub. So that's looking decent. So that, yeah, that's not a major change. It's just making that a little bit less noisy. And then lastly, back over here, so I'll just write my conclusion. AI strongly discouraged against the macro to generate a prototype plus naked function. Encouraged to simply use the .s stub. Okay, so no great way to reduce this boilerplate. However, the extern C log syntax helps. X macro list is is a bit too much here. Yeah, and over here, the summary is that used a .h define header, which can be understood by trap.s, and also used in C++. Unfortunate that we can't use inline const expr in the header, but it's not so important for these constants. Bring us to over here. So dispatch and the handlers. Yeah, and it's really not the worst thing in the world. I mean, so right now we just have this bag of functions in this. And even, I mean, really, handle trap entry point. That one is called by this other translation unit, but really, I think pretty much almost everything could be in the inline namespace, actually. Like all of these are conceptually private functions. None of these are external APIs or something. The external API is handle trap entry point, which is called by trap.s. But otherwise, everything here is a private function to this translation unit. So that can be, just make sure that compiles, but I'm pretty sure that does. Yeah, so everything is private, and so that's how this code looks. We have this single thing, the space, and maybe even the naming of this is a bit open to question. Oh, what's up? What's up, Penuka Internet? Yeah, feel free. Yeah. So, I mean, even thinking about naming, it's so easy to go fast and not think a lot about naming. But handle trap entry point, I think I tried pretty hard to name that in a way that was kind of clear. We're calling into the entry point for handling the trap, but then handle trap. Like, what does that really mean? It's really this dispatching thing. So maybe I'll rename it to handle trap dispatch or something like that, or dispatch to trap handler, because that's really what we're doing here. We're dispatching based off of the trap frame. And then here's where we do the dispatch, and we call these different handlers, and these are just these simple functions for the moment. And in a lot of cases, yeah, this might change in the future, but we're not doing anything wild. Also, what the hell is going on here? This is for the trap return. We should not be doing this, yeah. It was just yeah. Why were we doing this again? This should not be necessary. If I remove this, what happens? Good, I guess it still works. Okay, this is that should not be there. This is just the dump trap frame helper. So this is roughly the implementation of the code. It's pretty simple. It's not fancy at all. It doesn't use any objects, doesn't use any classes. Maybe it could, you know, maybe it could. It sort of works. Like, is there really a need for a class here? That's sort of the question. You can imagine a class, I'm going to call it interrupt handler hub or something weird like that. And then somehow we get, it's just sort of overkill, I think. There's no state here local to the, unless we have this dispatch table or something like this. And then these can be like private methods or something like that in the class. But yeah, I think that is going a bit too far. So okay, so the point of this stream was just to take a moment to reflect on the implementation and see how we can clean it up. And I'm pretty happy with like the time we spent on this. I think we've addressed some of these pain points. We at least looked into how we might improve this. Nothing crazy. We didn't do anything like super crazy in the end, but I think we just got it to a nicer place. So yeah, I think we're sort of coming up on time, and it's sort of time to think about what could be next. And so, to zoom out a little bit, what I've been doing for the past while is I would just consider it prototyping. Even for the past few months, all this has been prototyping work, like prototyping. I mean, we had the frame allocator, prototyping a bit of virtual memory stuff, which we eventually didn't really end up using because we ended up deciding to not, we ended up deciding to continue using the Limini page tables and not do this migration effort, because that's not really the most important thing to focus on. And instead I've proceeded with getting interrupts working on 64-bit, which they are now. And I would basically consider the prototyping fairly complete for these topics, which means it's time to actually kind of rewind a little bit and do it for real in production, and also just think about more generally what we want to do. And probably the next thing that comes next is thinking about tasks and scheduling, I want to say. If we just quickly come back to JOS, .c. So JOS spends a lot of time doing a lot of various kinds of initialization that we either don't need to do because we're using Limini, or that we are just not doing because we haven't gotten there yet. And so, for example, we don't need to zero out a BSS. Limini does that. We don't need to initialize a console because I'm using the Kimu debug port for the moment, and so there's just no console. I didn't want to write a console driver at this point, and so we didn't need to do this. We don't need to detect memory because Limini does all of this. We're not doing multi-boot 2. Yeah, memory management, we've got into a little bit of that. We haven't done any end user like environment or like task stuff yet because that will come next. We just finished basically this kind of trap stuff for the moment. And then multiprocessor, that is coming later probably. We haven't gotten there yet. The pick is interesting. When we want to do preemptive multitasking, we'll need to set up the pick. I don't even know how to, yeah. Then this is much more advanced stuff with I don't know, time or PCI and stuff like this. So I'm thinking, yeah, let's not dive into multi-core just yet, but since since interrupts are pretty much prototype, we're ready to start productionizing things a little bit. And this is just a peek of what I'm thinking we'll get into next time. But my vision is that this K main will look very different and probably a lot smaller. Yeah, my idea is like we're gonna have some kind of kernel class, and then this would be like kernel.run, and we'll just kind of like architect it that way. And then the main is gonna be very small. We're just gonna have this kernel object, and like it's going to take care of stuff, and maybe it'll own some memory allocators. Maybe it'll own an IDT or some interrupt or IO infrastructure or something like this. So yeah, I think that's sort of my idea. We just have like, I was just putting like a ton of messy code into the main just for prototyping and experimentation, but we've gotten to the point where things are working enough to clean that all up. And so we can take what we've learned through all this work and then start to actually do it in more of a real way. And it might look like just a bunch of moving code around, but there will certainly be opportunities to think about APIs and stuff like this. So that's sort of what I'm thinking. Alternatively, we could just go ahead and keep going and like just keep prototyping with like task switching and maybe some scheduling stuff, but that's not really feeling appropriate for me right now because, well, for one thing, the mess is just getting too much. It's just a huge mess. And then we would need to answer questions about like, where do we keep the state for the different tasks? And we might end up just using another variable on the stack here, which is starting to feel a little bit too sloppy for me. And so I think what we're gonna do, we're just going to kind of rewind a little bit, use everything we learned through like all this stuff, sort of re-implement it in a bit of like a cleaner way with an actual implementation that I wanted to explore with more of this kernel object or something like this. And then once we have that, we'll be in a bit of a better place to proceed with scheduling and some basic task switching, maybe even cooperative multitasking for the moment. Like we can consider not even having preemptive multitasking, like no timer, but just have a couple tasks that cooperatively yield to each other. And like, I don't know, do some basic computation, all still within kernel mode. I still have this kind of scope of like, we're just doing things within kernel mode for the foreseeable future. And then eventually, if we feel like it, we can get into user mode, but that's really not my key concern. So let me check the chat. Yeah, Ismail, will you look at other people's kernels? I think you were curious about NT Fuchsia. Yes, absolutely. We haven't gotten to that quite yet, but I'm interested in, what, like, they have this object model, which is quite interesting. Linux doesn't really have an object model, like this idea of kernel objects, and so I'm quite interested to learn about this kernel object idea. Although that's a bit more of a user space topic, like how does the kernel represent objects to user space, and what are the syscalls and APIs that look like for doing that? I can definitely imagine that we spend some time looking into that in the future. Yeah, so let me just write some of this down. So roadmap. And so prototype some VM stuff and interrupts. That's finished. I'll just draw the vertical line. Next up is go back and do some productionization work, cleanups, kernel object, etc. Maybe clean out these crufty JOS files that are still lying around. And then in the future, next is tasks, basic scheduling, cooperative. And then even further from that, we can think about preemptive multitasking with timer interrupt. Yeah, this stuff will naturally involve a bit of VMs, bit more of some VM stuff. At some point, we'll need to handle VM deallocation of frames. We simply just never did that. I only implemented functions for allocating pages. So this will be in there somewhere. Yup, that's the plan. All right. Well, that was just, yeah, another session. Thanks for joining me while I checked out some more of this interrupt stuff. That's going to be pretty much it for today. If you are watching right now, please subscribe to my YouTube channel. If you enjoy this content, we'd appreciate that. And then also feel free to join the Discord if you want to hang out and talk some more. And with that, that's going to be the end of today's stream. Thanks a lot for joining. Good to see you, Ismail. And I will catch you all next week. Peace.